What specific problem does your proposed SGP bench aim to solve in the context of LLMs understanding symbolic graphics programs?
The proposed SGP bench aims to solve the problem of evaluating the semantic understanding of large language models, LLMs, regarding symbolic graphics programs, specifically focusing on their ability to answer semantic questions based on the corresponding rendered images. By establishing a benchmark that includes two types of evaluations, semantic understanding and semantic consistency, SGP bench assesses how well LLMs can comprehend the meaning of symbolic graphics programs and maintain that understanding under perturbations of the program code. This benchmark is particularly significant as it addresses the challenge of determining whether LLMs can imagine the visual output of these programs and understand the procedural nature of graphics generation. Furthermore, SGP bench provides insights into the reasoning capabilities of LLMs, revealing their strengths and weaknesses in understanding complex symbolic structures. Overall, it contributes to a deeper understanding of the limitations and potential of LLMs in the domain of symbolic graphics program comprehension.
Can you illustrate step-by-step how the Symbolic Instruction Tuning (SIT) method works to improve ILM's understanding of symbolic graphics programs?
The Symbolic Instruction Tuning (SIT) method improves ILM's understanding of symbolic graphics programs through a systematic process. First, it generates symbolic instruction data by leveraging rendered images from symbolic graphics programs, prompting a powerful vision language model, e.g., GPT-4o, to produce semantically rich descriptions for each image. This step creates a dataset containing detailed semantic descriptions for 55,000 symbolic programs. Next, the method involves supervised fine-tuning of open-source LLMs using this instruction dataset, which enhances their ability to understand and reason about symbolic graphics programs. Experimental results demonstrate that this fine-tuning consistently improves the performance of LLMs, as evidenced by an increase in accuracy from 46.7% to 51.4% for the LLAMA3 1-8B model, indicating that SIT effectively bridges the gap between semantic understanding and symbolic reasoning.
Could you provide a simple example that demonstrates the process of generating semantic questions from a rendered image of a symbolic graphics program using your proposed method?
To generate semantic questions from a rendered image of a symbolic graphics program, we utilize a vision language model, such as GPT-4o. For instance, consider a symbolic graphics program that produces a rendered image of a red circle. We would first render this program into a 2D image. Next, we would query GPT-4o with this rendered image to generate semantic questions, such as what color is the circle, or how many shapes are present in the image. After generating these questions, we manually inspect them to ensure they are reasonable and that the answers are correct. This process allows us to create a scalable dataset of semantic questions linked to the corresponding symbolic graphics programs with minimal human effort, as detailed in the paper.
What are the key advantages of using SGP bench compared to existing benchmarks for evaluating ILM's capabilities?
SGP bench offers several key advantages over existing benchmarks for evaluating ILM's capabilities. Firstly, it specifically targets the semantic understanding of symbolic graphics programs, such as SVG and CAD, which is a novel area not extensively covered by prior benchmarks. Secondly, SGP bench employs a scalable pipeline for generating semantic questions based on rendered images, significantly reducing human effort in question creation, while ensuring high-quality outputs through automated generation and manual inspection. Additionally, it includes a semantic consistency evaluation that tests ILM's robustness against perturbations in the symbolic programs, providing insights into their foundational understanding rather than mere memorization. Lastly, SGP bench facilitates the assessment of various reasoning abilities, from attribute-level investigations to higher-level semantic reasoning, making it a comprehensive tool for evaluating the holistic reasoning capabilities of LLMs.
How did you validate the efficacy of the SGP bench? And what metrics or benchmarks did you employ to measure the performance of the models tested?
The efficacy of the SGP bench was validated through a comprehensive evaluation process that included two main types of assessments: semantic understanding and semantic consistency. For semantic understanding, we constructed multiple-choice questions based on rendered images from symbolic graphics programs, which were then used to evaluate the model's ability to answer these questions accurately. The performance of the models was measured using accuracy metrics, with results indicating that most models achieved below 65% accuracy on SVG and below 80% on CAD. To assess semantic consistency, we introduced perturbations such as random translations and rotations to the symbolic programs, ensuring that the semantic meaning remained unchanged while altering the code representation. The model's consistency in answering the same questions based on these perturbed inputs was measured using average accuracy and a proposed consistency score, which indicated how consistently the models maintained their predictions despite significant changes in the input code.
What significant insights did you gain from the performance results on the SGP bench, particularly regarding the challenges faced by LLMs in understanding symbolic graphics programs?
The performance results on the SGP bench revealed that understanding symbolic graphics programs is a significant challenge for large language models, LLMs, with average accuracies below 65% for SVG and below 80% for CAD programs. Notably, SVG programs posed even greater difficulties due to their richer semantics, as evidenced by the models achieving only chance-level performance on the SGP MNIST challenge, despite the rendered images being easily recognizable to humans. This discrepancy suggests that LLMs process symbolic graphics programs differently than humans interpret images, highlighting a gap in their semantic understanding capabilities. Furthermore, while proprietary models like GPT-4 outperformed open-source counterparts, the overall performance gains aligned with the scaling law, indicating that larger models tend to have better semantic understanding. These insights underscore the need for further exploration into the reasoning mechanisms of LLMs and the development of improved training methods to enhance their understanding of symbolic graphics programs.